Welcome to the wonderful world of astronomy. We're in Chapter 1, A Modern View of the Universe, and this is Part 2, Seeing into the Past. A very interesting part about astronomy is that we can actually see into the past. The farther away we look, the further back in time we are looking. The reason is that whenever you see anything, whether it's things that are in your room or things up in the sky, there's time that light takes to get from that object to your eyes. And so the farther away you look, the more time it took for the light to reach your eyes. For example, if you hold your hand out in front of you, the light from your hand takes about 3 nanoseconds to reach your eyes. So a nanosecond is a billionth of a second. You're seeing your hand. We think of it as you see it as it is this instant, but really the light took 3 billionths of a second to get to your eyes. So you're seeing your hand as it was 3 billionths of a second ago. Now, 3 billionths of a second is such a short amount of time that it just seems instant to us. And things that happen on Earth, the light takes such a short time to get to us that it's pretty much instantly that the light gets to us. So we see things on Earth in real time. But when we start to look up in space, the distances get farther. For example, the moon is such a distance that it takes about a second to reach the Earth. So whenever you see the moon, you're not actually seeing it as it is right now, but you're seeing it as it was a second ago. There's a 1 second delay because of the time it took for that light to go from the moon to your eyes. And the moon is the closest astronomical object to Earth. Let's go farther out. The sun is much farther out. It's about 93 million miles away, and it takes light about 8 minutes and 20 seconds to travel that 93 million miles. So when you see the sun, you're actually seeing it as it was 8 minutes ago, which means if you want to know what the sun looks like right now, you have to wait 8 minutes for that light, that information to travel across the 93 million miles to get to us. And that brings up a unit of measurement that we use in astronomy, 1 astronomical unit, and we abbreviate that AU. It is, by definition, the average distance between the Earth and the Sun, 93 million miles. Later on, we will look at, you notice that it says average distance. Sometimes the Earth is a little bit closer, around 91 million miles. Sometimes it's a little farther, like 95 million miles. But on average, 93 million miles. That's 1 astronomical unit. And it takes light about 8 minutes, a little over 8 minutes to travel that distance. So we can also speak of it as a distance of 8 light minutes. Light to get from the planet Mars to Earth takes somewhere between 4 to 21 minutes. Now that's a wide range, between 4 and 21 minutes. And the reason is that the Earth and Mars are traveling around the sun, and we are relative to each other in different places at different times. So here the blue circle represents the Earth, and when Mars is in direct line with the sun and Earth on this side of the solar system, it's not that big a distance away. So it's about 4 light minutes. Light takes about 4 minutes to get to the Earth. But other times in the year, when Mars is on the other side of the sun, then the light takes 21 minutes to go all the way across. Saturn, depending on where it is in the solar system relative to us, the light takes about 1.3 hours to get to us. So we are looking at farther and farther objects in this slideshow, and so Saturn is farther out. Pluto, which used to be the farthest planet from the sun until it got declassified as a planet in 2006, it is about 4.4 light hours from Earth, meaning light takes 4.4 hours to reach the Earth from Pluto. We sent a spacecraft called New Horizons to Pluto, and it got there in the year 2016. And it was beaming back much information, lots of photographs and other information about Pluto. And that information traveling at the speed of light took 4.4 hours to get to us. The spacecraft New Horizons took almost 10 years to get from Earth to Pluto, 10 years by rocket propulsion, but the light that it sent back, the information it sent back, only took about 4.5 hours to get back to us. And this brings up another unit of distance that you need to know for studying astronomy, a light year. It's the distance that light can travel in a vacuum in 1 year. Now, in parentheses, I say in a vacuum because that just means in the emptiness of space. If light actually goes through some material like water or glass, it actually slows down a bit. But through empty space, that's what a vacuum is. It goes in 1 year, it can travel 9.46 trillion kilometers or 5.88 trillion miles, and that's a light year. Notice I underline the word distance because when people hear the word light year, they hear the word year and think we're talking about a unit of time, but it is a unit of distance. So as we move out beyond the solar system, we've got the closest star to Earth. It's called Proxima Centauri, and it is 4.2 light years away, which means when we see it in the sky, we are seeing it as it was more than 4 years ago, because we're seeing the light that left that star 4.2 years ago. It's been traveling across space, and finally, more than 4 years later, it gets to us. All these stars that I'm showing you right now in this slideshow, you don't have to memorize this and these numbers. I'm just giving these as examples of things in space. This is a constellation Gemini, or the two most prominent stars in the constellation Gemini, known as the twins. And they are Pollux and Castor. The one on the left called Beta Geminorum, and Castor is Alpha Geminorum. So Pollux and Castor. And while they look close to each other in the sky, they're actually different distances from us. So Pollux is 33 light years away. That means that we are seeing it as it was 33 years ago. And Castor is 51 light years away. So we're seeing it as it was 51 years ago. The light has been traveling across space that long. So you see, we are seeing into the past. We're not seeing them as they are now, but rather as they were that many years ago. I also want you to notice that these stars have different colors. Pollux is yellow and Castor is blue. And later on in the semester, we'll talk about why stars have different colors. Moving farther out into space and therefore further back in time, there's a double star named Albireo, or Beta Cygni, and when it was first discovered in ancient times, it's a pretty bright star, so people have known about it since ancient times. It was thought of as one star. But with the invention of the telescope, it was then realized that it's actually two stars, which in part explains why it's so bright. It's really two stars. But it is 434 light years away. So now when we look at it, we are seeing it far back in time, 434 years ago. And so if these stars were to explode, go supernova, and these stars are not at risk of doing that anytime soon, but if just take, for example, one of these stars, if it had blown up even 200 years ago, we wouldn't know about that for another 234 years because the light from that explosion takes 434 years to get to us. All we can see is what it looked like 434 years ago. If we want to know what those stars look like now, we have to wait 434 years. And Albireo, by the way, is in the constellation Cygnus, and that's a constellation that is up high in the sky during the autumn. And there's Cygnus, it's the swan. There's the Milky Way in the background, and we'll talk about that later. But the swan is as if it's flying through the Milky Way, and Albireo is actually the head of the swan. The constellation Rigel, otherwise known as Beta Orioni, is 772 light years away. So when we look at it, we are seeing it as it was 772 years ago. And Orion is more of a springtime constellation, and there's Rigel. It's the foot of the hunter Orion. Looking farther out, still staying within the Milky Way galaxy, but looking farther out, we have the Butterfly Nebula, named because it has a butterfly-like appearance, 2,100 light years away, so we're seeing it as it was 2,100 years ago. Moving farther out, the Rosetta Nebula, 3,000 light years away. So we're actually looking back to a time of about 1000 BC. Moving farther out, yet still staying within our galaxy, is a globular cluster known as M13. It's a cluster of about 1 million stars that are all tight together, all in orbit, mutual orbit around each other. It's 20,000 light years away, and so we're seeing it as it was 20,000 years ago. Now, at this point, you might be wondering, how do we know how far away these things are, what these distances are? And that is something that I will answer and we will see as we progress learning in astronomy class. So by the end of the semester, you'll have a clear picture of how we know the distances to these things far away. And then we can leave the Milky Way galaxy and look at other galaxies. The Andromeda galaxy, which is a relatively nearby galaxy, is about 2.5 million light years away. So we are looking at it at a time when it was, or at a time 2.5 million years ago. Now, a really neat thing to contemplate is if you think about the front of the galaxy in this picture and the back in the background of the galaxy, that's a diameter of about 100,000 light years. So there's a time difference between the front and the back. There's a gap of 100,000 years time between the front and the back. So just looking at this picture, it's all happening, or it all happened at different times. And we move beyond our local group of galaxies to the Virgo cluster, which is about 60 million light years away. So we're seeing it as it was 60 million years ago. And then we look out to the farthest reaches that telescopes can find, and this is pretty much the limits. This is about 13 billion light years away, this little square here. And then in this square, they've zoomed in at a particular galaxy. So looking at that galaxy and looking at these distances of about 13 billion light years away, we're seeing the very first galaxies in the universe. So when we think about astronomy and looking at things in astronomy, far away means back in time. The farther we look, the further back in time we're looking. Light travels at a finite speed, about 300,000 kilometers per second. So as I just showed in the previous slides, to get to the moon, or between the moon and the earth, light takes about 1 second. From the sun, about 8 minutes. From the star Sirius, that's the brightest star in the sky besides the sun, so the brightest star in the night sky, it's about 8 light years away, so we're seeing it as it was 8 years ago, and that's a star that we see more during the springtime. And the Andromeda galaxy, it's about 2.5 million years time. So it will be important throughout this semester to understand that, again, here it is in bold print, the farther away we look in distance, the further back we look in time. Here's the Andromeda galaxy. This map here of the sky, it shows the Pegasus constellation and Andromeda and Cassiopeia. And there's the Andromeda galaxy. And this is how it looked 2.5 million years ago. And again, if you want to know what does it look like now, we have to wait 2.5 million years for that light to get to Earth. But maybe by that time we'll have made our way closer to it, so we don't have to wait that long. So again, when will we be able to see what it looks like now? 2.5 million years, unless we start traveling towards it. some math to show how far is a light year. Well, 1 light year is the speed of light times 1 year. So that's just the distance is the speed times time. And I'm not going to ask you to reproduce this on the test, but just so you can see where we get this from. So the speed of light is 300,000 kilometers per second. And we're going to multiply that by a year. And we can say 365 days over a year, 24 hours over a day. We're doing the unit conversion here, 60 minutes over an hour, 60 seconds over a minute. Basically, all this is unit conversions so that we can get it in seconds or get rid of the seconds. And so we get, in the end, 9.46 trillion kilometers, which is about 5.88 trillion miles. Can we see the entire universe? The answer is no. If you think about the entire universe as it's been expanding since the beginning, and there are many, many stars, many, many galaxies, but we can only see out to a distance of about 13.7 billion light years. And the reason is that the light has been traveling for only 13.7 billion years. So there's a point at which there are undoubtedly galaxies beyond it, but we can't see that far because the light from those galaxies, such as that yellow one right there, just imagine that we are at the center where my red marker is right there. There really is no center of the universe the way the universe is expanding. But in this picture, we're at the center of that circle where my red marker is. And over to the right, that galaxy that's shown, it's far enough away that its light has not had time to get to us yet. So this blue circle represents what's called the observable universe, everything on the inside. And it's just all the things in the universe that light has had time since the beginning of the universe to get to us so we can see. And everything outside is the unobservable universe. We don't see those things that are on the outside. So as we look far, let's say here's an observatory, a little telescope in a dome there, and we look to something 7 billion light years away, such as right here. We see a galaxy 7 billion light years away, as it was 7 billion years ago, when the universe was about half its current age of 14 billion years. We look farther, 12 billion light years away, and we're really talking about the extremes of what we can see. We see a galaxy 12 billion light years away as it was 12 billion years ago, when the universe was only about 2 billion years old. And here we have, right here, the limit of our observable universe. Light from nearly 14 billion years away, light years away, shows the universe as it looked shortly after the Big Bang, before galaxies existed. Beyond the observable universe, we cannot see anything farther than 14 billion light years away because its light has not had enough time to reach us. So a thought question, assuming the universe is 14 billion years old, why can't we see a galaxy 15 billion light years away? And the possible answers are A, because no galaxies exist at such a great distance. B, galaxies may exist at that distance, but their light would be too faint for our telescopes to see. Or C, because looking 15 billion light years away means looking to a time before the universe existed. And the answer is C. That's the end of part 2, Seeing into the Past. Have a great day.